how to pronounce the name of the university, Université Côte d'Azur.
Excellent. Thank you very much, Mr. Chairman. So I'm going to talk about fast computation of steady surface wave, and I will more focus on long waves. So first I would like to acknowledge my collaborator, Denis Dutic from the University of Chambéry in France. So the motivation for this work was to understand steady water waves, gravity waves in arbitrary depths, and more specifically in shallow water, but not only. There are a lot of properties that are unknown about these waves, and not only for extreme waves, even for moderate amplitudes. There are still open questions about, for example, the monotonic variation of pressure or of acceleration field, or these kind of things mathematicians are interested in. Not so much physicists, but mathematicians are more into that, making rigorous proofs. And having, even for steep wave, having accurate computation, numerical solution is important in order to guess, check the property of the numerical solution to see if the conjecture you can make is verified or not. So having arbitrary precision is a strong argument, because if you have only few digit accuracy, you never know if it's a numerical artifact or if it's a true solution. Of course, having arbitrary precision is not a formal proof, but it just help to build confidence about the results. There are practical situations where accuracy is needed, for example, for studying stability of waves. So you want to have a steady wave of traveling with constant speed of the permanent form, and you want to perturb it to see the stability. And if you want to have an accurate prediction of the result, you need also an accurate initial condition. Because for long-time simulation, if your initial condition is not exactly what you think it is, it will evolve differently, and you may draw some wrong conclusion about the phenomenon. I did such a simulation, and I observed that differences. So, like if you have in initial conditions some differences at the 6th digit, it will may diverge quite rapidly. So it's important, for example, for this situation. The problem with accurate computation is that they require a large number of computational nodes or Fourier modes if you use Fourier decomposition, especially in shallow water. Why? Because you know that waves have a different crest and trough. They have sharp and narrow crests and quite flat and long troughs. And in terms of Fourier decomposition, it means that you need a large number of Fourier modes to capture well this profile. So, since you need a large number of computational points, you need a faster algorithm to compute the solution. If not, you will pay an heavy price. So, if you look in the literature, there are several numerical models. I just listed a few here that are accurate for steep waves. They were designed to study the highest waves. And just you have a few lists here, and you can look in the review, in the books by Okamoto and Shoji, and the one by Jean-Marc, if you want more details about all the models and the technique. The problem with these schemes, and there are practical algorithmic complexity of order n cube, or somewhere between n square and n cube, where n is the number of nodes or the number of Fourier modes. Most of these algorithms use Newton methods, or Levenberg-Markov algorithm, this kind of algorithm for solving the system of a nonlinear equation. You end up with your numerical model. Newton method has a theoretical complexity of order n squared, but this is a minimum complexity when you use some implicit scheme. In the most robust implementation, the resolution, you have to invert some, to compute some Jacobian matrix to solve some nonlinear system, and the robust implementation normally is the QR algorithm decomposition that has a complexity of order n cube. So an example is the function fsolve in MATLAB, which is very good nonlinear solver, which has complexity of order n cube. The problem is that when n is big, n cube or even n squared may be prohibitive. So, yeah, they may be prohibitive because the computation may be too slow. They may accumulate a large number of random error. The more you compute, the more error you accumulate. That can lead to also badly conditioned system. That depends on your algorithm and how it is implemented. And you can get some numerical instability. For shallow water waves, so shallow water, I mean waves such that the wavelength is long compared to the water depth. You can use some called Knoidal wave decomposition. Instead of using Fourier series, you use elliptic Jacobian function, and you do this kind of shallow water expansion. The problem is that these expansions, they are divergent. The radius of convergence is 0. That's the first point. So you can get only limited accuracy with this expansion. And moreover, you have to compute the Jacobian elliptic function, and this has a cost. And for very long wave, you may have numerical problem to compute that. I will come back to this point at the end. So an alternative is to use Petyaashvili iteration, which this algorithm has order n complexity. So it grows linearly with the number of unknown. So it's a big improvement compared to Q1 squared. So just a brief summary of the Petyaashvili method. When you have your PDE describing nonlinear waves, for instance, and you are considering traveling waves of permanent form, you end up with an ODE that you can split in linear and nonlinear part. You put the linear term on the left-hand side, the nonlinear term on the right-hand side. And that's the beginning. So for example, if you have a KdV equation, I guess everybody here knows KdV. The linear part is this advecting term plus dispersion term, and the nonlinear term is like that. And for such an equation, the linear part is an autonomous term. So it can be computed easily in Fourier space. So if you apply this linear operator to a pure frequency, you end up this pseudo-differential operator ends up to be just an algebraic multiplication in Fourier space. So it's very easy to compute, and it's also very easy to invert. So if you invert the linear operator here, you will have eta as a function of eta, and you can apply a fixed point iteration. So that's the naive fixed point implementation here. But if you do that, it will not work. I mean, 99.99% of the time it will not, unless you are very, very lucky. So Petyaashvili idea was to introduce a stabilizing multiplicative factor S at the power 2, where S is defined like that. So you project your unknown against the linear operator and against the nonlinear one, and you compute the ratio. When eta is a solution of the equation, S is equal to 1. So at the end, you end up with the solution of your equation. And Petyaashvili did that for computing solitary wave of, I don't know what kind of equation, Petyaashvili. And
what kind of equation?
Petyaashvili, KP.
KP. Okay.
It's easier, KP. So the advantage of this method is that this term is a scalar. Okay? So it's very simple, very easy to implement. You don't have to build any matrix, you don't have to solve a linear system. It's just stupid fixed point iteration. And it's also very easy to implement in higher dimension. If eta is a function in 2D, 3D, basically it's the same. Yeah.
So just one question. So I've only seen that in the context of solitary wave.
Exactly.
But I mean, so what if you have periodic wave?
But this is what I'm talking
Okay.
about.
Okay. Right.
Be patient.
Okay.
So actually, this algorithm is very fine and it's unbeatable when it works. And it doesn't work all the time, actually. It has quite stringent conditions. So typically it works when you have homogeneous nonlinearity. So if your right-hand side is only a cubic term or only quadratic terms, but when you have a mixture of them, it's more tricky. And it has been implemented for solitary wave to compute solitary wave and solitary wave solution of a Toyo equation like KdV, KP, or Kamasaon, nonlinear Schrödinger. Okay. And it was used for a long time by Stepanians, and Pelinovsky and Dimitri here they made some theoretical study, investigation of this scheme, why it works or not. But they did it on a very special equation. And theoretical results are lacking for this scheme. And this is one motivation for my presentation, is to invite mathematicians to investigate further why it works or when it doesn't work in order to understand it and to improve it and these kind of things. And there are also some results by Alvarez and Duran. If you have a theoretical question about the Viashvili method, you should ask Dimitri, not me. So in order to apply this kind of simple iteration to a broader class of equation, some modification of generalization have been proposed. So here I listed some. And another related one is called the accelerated imaginary time evolution equation. And if you go to Young's homepage, he has a lot of review and nice example of that. So I invite you to look at this web page for more information. So the strategy here was to modify the method in order to apply it to the equation that people have to solve. And I wanted to do the other way around. I wanted to modify the equation such that I can apply the basic equation. That is Euler free surface and Euler equation. Okay, that's what I want to explain to you, how you can adapt this method for computing free surface waves. So here it's the classical equation for 2D steady irrotational surface gravity waves, where the velocity potential phi is a harmonic function. It satisfies the Laplacian. And when you have a 2D problem with harmonic function, the first thing you want to do is to use complex variable and complex function. At least this is what I like to do. So if you introduce a complex abscissa and a complex potential, where you introduce psi, it's called the string function, is the harmonic conjugate of phi. And this velocity potential and string function are related by the Cauchy-Riemann relation and the velocity field here. And this Cauchy-Riemann condition implies that f is a holomorphic function of z. Since the flow is steady, the free surface is a streamline. The function psi is constant at the free surface, and it's also constant at the bottom. So instead of solving the problem in the physical space where the domain with the free surface is unknown, okay, a good idea is to reverse the problem and to take f as independent variable instead of z. So it's called conformal mapping. So what I do, I introduce a change of independent variable where I introduce zeta is minus f over c. Or why is that? It's because I want to have the conformal plane oriented in the same direction as the physical plane. So I want the right in the physics to be the right in the conformal and the up being the up. So the minus sign here. And there is a scaling factor c that has the dimension of a velocity that I choose in a particular way. When you do conformal mapping, your physical box has a certain wavelength and a certain depth. When you map, you get a rectangle, but the wavelength in the map domain and the thickness or the depth, if you want, in the conformal plane are different from that of the physical plane. And you can fix one of those, but you cannot impose both. So I choose C such that the period, the wavelength, is identical in the physical space and in the map space. But then, if I write my conformal variable alpha plus beta, the free surface is beta equals 0, and the bottom is at beta equal minus d bar, which is different from the original depth. And this is unknown, and it depends on my solution. So I have to compute this parameter. It's part of the problem. Of course, from a programmation point of view, you could fix the thickness of the domain in the conformal plane. But then if you do that, when you compute two different solutions that have identical thickness in the conformal plane, they have different depth in the physical plane. And normally when we compare waves, we want to compare with the same quantity of water. Okay? So if you use that simple mapping, it gets simple, apparently simple formula, but then you need a heavy pre- and post-processing to transform your physical data into the computational one. You process the data, and the computational results, you have to process it to get into the physical plane. I mean, we are going to deal with reality. We want to solve a problem with quantity that are accessible to the real world, not defined in an abstract space. So it's better to do it in the first place by defining this kind of variable that way. It's not obligatory, but it's simple. Because we had in mind to write a code that can be used by people. And the experimentalist, he has experimental data, he wants to give that to the program, and he wants to get physical answer. He doesn't want to make some crazy computation, because all these definitions are more or less implicit. So it's better if the program does everything by itself. Okay, so that's the main idea. So to make a sketch, I'm sorry, I didn't have time to make a nicer looking sketch, but basically your free domain is like that, and you map it into a strip and see what that was for solitary wave, but when it's a periodic wave, you just have a rectangle here. Okay. From that point, you process the equation, you make the transformation, you have to introduce all the relations that define your physical quantity, the mean water level, the mean depth, everything. So it's quite some calculus, it's difficult, but quite some calculus. So I will spare you all this algebra. You run the crank and you end up with an equation that is called Babenko equation. So y tilde of alpha is the equation of the free surface in the conformal parametric variable. Okay, it corresponds to the free surface, and it involves a parameter that is unknown. That's the ratio of the conformal and physical depth that you have to compute, and it involves a pseudo-differential operator here, and K1 is an integration constant. So it's written that way. Here we have linear term, non-linear term plus a constant here. I'm not here. If this operator is written here as a pseudo-differential operator, but you can also write it as an integral, convolution integral, that is should be a pair singular integral. But the simplest definition is when it's applied to a pure frequency, it just gives this quantity that is very easy to compute in Fourier space. It's just an algebraic multiplication. And from a computational point of view, multiplying your unknown by this quantity or by k or k cube, it's the same thing. So from a computational point of view, this equation is not formally more complicated than KDD. Okay. Computational point of view, not analytic mathematical. The point is not to prove theorems. So you start with this equation and you want to compute numerically your wave. And we did that for solitary wave, and it worked very fine for solitary waves. And we have published works on that. But then we noticed that it doesn't work for periodic wave for some reason I want to explain to you. So I think it's Yachenko et al., they use a modified Petriashvili method, and they managed to compute periodic wave in infinite depths at deep water. But if you use their algorithm on finite depths, it doesn't work for some reason. Okay? And I was wondering why, because when you compute solitary wave, actually the domain is infinite, but in practice you periodize the box. So when you compute a solitary wave, you compute a periodic wave. Okay? So why it works for a periodized solitary wave and it doesn't work for a periodic wave? I was puzzled. So there are theoretical question for that. Ask Dimitri again. I will just explain my feeling why it didn't work. And the question I ask myself is, what are fundamentally the difference between a solitary wave and a periodic wave from a computational point of view? The difference is that solitary wave have a wave mass. A periodic wave is normally it's defined as a periodic oscillation around a mean level, so the average is 0. While a solitary wave has a 0 average when the box is infinite. But in numerics, you never go to infinity. So when you compute numerically, the average is not 0, you have a finite mass. Okay? So my idea was to say, okay, then my periodic wave, if I just move down the mean value to the minimum, it will look like a solitary wave. Okay? So instead of solving the Babenko equation for the primitive independent variable y, I just subtracted the minimum and I introduced a new variable epsilon. Okay? This is all. I just changed the 0 value. Of course, I tried that case, but you could, there are probably other intermediate value that make it work. So you apply the Petit-Hachini method. So for this special form of the Babenko equation. And shifting the unknown doesn't matter that much for the linear and nonlinear part, but it matters for the stabilization factor. Because now, here, this quantity is always positive. Okay? So there are less cancellation. I cannot, it's just a gut feeling what I'm telling you. Huh? It's the way I understand it, but I cannot prove. So I think when you have a solution oscillating around zero, you may get cancellation, and you very too small or badly conditioned, I don't know what I should say, stabilization factor. Okay, so that's the only difference I see between the two. And as an initial guess, I just start with a sinusoidal wave of the wave height I want to have. For whatever wavelength, I don't bother to make continuation, I just fit that and I let it, I iterate. And it works. And it works for arbitrary depths. So first I have to, before I show you the result, I have to define the parameters. Normally physicists, they like to define a wave by the steepness, that is half the total wave height multiplied by the wave number. But this parameter is not suitable in shallow water. In particular, if you take a solitary wave, k is 0, so epsilon is 0 for all solitary waves. So it's a good parameter in deep water, but it's not a good parameter for long waves. And you can, we define as well the wave by the dimensionless wave number. But when you are dealing with long wave, it's better to define the wave by this other set of parameters, that is the wave height divided by the depth, and the wavelength divided by the depth. But the same, this one is not valid in infinite depths. Actually, you can find a pair of parameters that are valid for arbitrary depths and arbitrary wavelength, but they are not simply connected to physical quantities. So that's why I didn't do that, but you could do it. Okay. And again, as I said, I use that because users want to feed the machine with that pair or that pair. Okay, so you do that in infinite depths, and it works fine for every steepness less than 0.44. If you compare with the Fenton algorithm, that is limited by 0.36 and Yatchenko by 0.436. This is not the highest possible wave. So when you exceed this limit, so here, for example, I just a little bit exceed this limit, and if you use 1000 Fourier mode, you see a nice steep wave, but if you double it, you get a spurious solution. So the algorithm converges, but it converges to what's called ghost solution sometimes. So why?
How high is your steepness defined? Difference of height between
What total wave height divided by 2 times k.
Time k, yeah.
Time k. Sometimes it's
so the highest wave would correspond to what?
highest about 443, I guess.
Oh, okay. It's, yeah.
So it's not that far from the.
Yeah. Okay.
And to understand what's happening is that you have to compute, for example, physical quantity like the Bernoulli constant as a function of the steepness. And when you increase the steepness, this parameter increases, but it reaches a maximum. And then it will go down and go up again. And when you are in this region here, when you fix the abscissa here, the algorithm doesn't know which branch of the solution to take, so it doesn't work. That's why we observe this bizarre phenomenon. Okay, and this is natural. So if you want, with Petit-Hachini method, if you want to exceed that point, you have to define your wave by another set of parameters that will give you a unique solution. But again, these parameters are not simply related to physical quantity, so I didn't explore that yet. But I think you can exceed that up to the next non-unicity and so on and so on. Okay, this corresponds to a maximum of energy in wave. That's the maximum you can observe in the wave tank. So all these solutions are of physical interest. Going beyond that is more of theoretical and fundamental interest. So let's take, still in deep water, a steep wave, 0.4. 0.4, it's a steep wave. You don't meet them all the time. And I want to illustrate the robustness of the algorithm computing this solution with 512 Fourier mode. And here is the Fourier transform in the log scale of the free surface. And you see an exponential decay of the Fourier mode down to the machine precision. Here it's double precision computation, so the minimum is around 10 to the power minus 16. Okay. So it means that here you have reached spectral precision. If you put more points, you will not gain any accuracy. You are the maximum you can get with this floating point format. What is more interesting is that if you double the number of points, okay, you have saturated your spectrum in double precision, but the algorithm remains stable. There are algorithms like Fenton program. If you put too many Fourier moves, it will become unstable numerically. Here we don't have this problem. Of course, I don't gain any accuracy. I stay around machine precision. But if I do the computation in quadruple precision, my spectrum continue decaying down to quadruple precision. Machine precision, that's about 34 digits. But then if you still double, again you double the number of points, your double precision computation remains stable, quadruple stable, and octuple precision you can go down. Okay, and you can easily compute hundreds of digits if you want to. I don't know what for, but you may want that. No, but in mathematics, to check some conjectures, it's important sometimes to have digits. Okay.
No, so this steepness, is that already, I mean, do you get some crest and stabilities already there yet?
No, it's after the maximum.
Oh, after the, okay.
You mean the oscillation?
Yeah.
No, it's
Okay.
I'm talking about under the control of Lamarck, but I think it's for higher way. It's very close to the maximum one. This algorithm was not designed for that. I'm currently working on this problem, but it will be a completely different algorithm. So you have to design to tailor your algorithm for your goal, for your purpose. Okay. Let's have an example in finite depth. KD equal 1, and I took 2000 modes. For epsilon equal 0.3, and you have a rather steep wave. And again, the spectrum is going down to machine precision. And if you increase the parameter by a little bit, you have a steeper wave, and of course, you don't reach machine precision. So why? It's because epsilon, as I said, is not a good parameter for long wave. So the shallower the water, the more narrow is the range of variation of the parameter epsilon. So actually, epsilon 31 and 30 are quite different waves, and you see that the steepness here is quite much important than here. So if you want to compute the solution to machine precision, it's easy. You just have to take 8,000 points. You will get it. 8,000, it's easy. We'll see more than that. Okay, so now let's go to very long waves. The algorithm, I repeat, is working for any wavelength. So you cannot do that with the algorithms I know, the program I know, because they are too slow, or they are unstable, or both. And for example, with Phantom program, you are limited to a ratio of length over depth of around 50. And if you go to his wave page, you will see he computes such a wave, but there are spurious oscillations. I have to say, I'm nothing against Phantom. I mean, I'm referring to his because his programs are available, and I could use them, and I can compare, so I know what I'm saying. And I have a lot of respect for his work, and they've been helping me a lot. So, but if you use the Babenko equation plus the spectral method and Petriashvili iteration, they work fine for any ratio. And by any, I mean any. So let's compute a wave 1,000 times the depth. Okay, it's a bit bigger than 50. And h over d 0.4, it's quite it's a decent wave. And if you use here 8,000 modes, you reach spectral precision. Okay. Now, I consider a bit shorter one, but much more extreme. I'm very close to the maximum. Remember earlier I mentioned the limit of the deep water because the energy is not increasing monotonically. You have the same problem on finite depths, but the limit depends on the depth. So I don't know. I didn't make a drawing to find exactly the limit, but you have the same phenomenon. So here I use 130,000 points to compute this wave, and it's quite steep. And so that's the free surface, the spectrum, and this is the surface plus the minimum in log scale. And you see that here you have reached the zero machine. So it means that from a numerical point of view, this is actually a solitary wave. So you can just use this solution and just adjust the depth to renormalize your depth, and you can use it to compute a solitary wave. For this computation, if you use Newton n square method, assuming that you can, it will take, I don't know, 1 year or something like that. Okay. It will cost you a lot. So now you may be an engineer and say, okay, me, I don't care about spectral accuracy, I'm an engineer, KDV is good enough for me. Okay? So here is KDV, analytical solution for traveling a long way, which is expressed in terms of Jacobian function. But what is important here is that this Jacobian function, they involve a parameter m that can be seen as a Nurser parameter for those of you that know that. The problem is that this parameter, an engineer, you want to fit the wavelength and the wave height. So you have to compute m by solving these relations, this kind of dispersion relation, if you want. And m equals 1 for solitary wave, goes to 0 for sinusoidal wave. But for cnoidal wave, a long wave, m is very close to 1. And how close to 1? That depends on the amplitude. But let's look at this one. 0.1. It's a small wave, but it's not an infinitesimal wave. If you so for different lengths, I compute 1 minus m, so we see how close it is. For 100, you will have already problem computed that with numerical double precision. 1000, you cannot do it. And if you go on to 1 million here, to get this number, I had to use alpha million digit to compute this number. You cannot get it. So you can now, but it's difficult to solve, to compute the solution from the analytical solution. Actually, it's simpler to compute the solution from the equation. So you could use PTHE method to compute the solution here. Okay, that's one option. But if you do PTHE method for KDV, why not doing it for Euler? Because it's basically the same thing. Or you can make some analytical approximation, investigation, but still you have to represent these numbers with your numerical format. So you have to work. So you have a simple analytical solution that you have to work a lot to get a numerical value. Just work on the original problem. Of course, this problem is increasing when the height is increasing. Okay? So if you take 0.5 here now, you see how m goes close to 1 as the wavelength increases, and 100 is not that much, and you are already here. You are already, from here, you are already beyond machine double precision. Okay. So here I've been showing an extreme case. Okay? But let's compute that with the Babenko equation and the PTHE iteration. So this is what I do here. In double precision, I use 2 millions positive Fourier modes, and I obtain spectral convergence after 74 iterations in less than 2 minutes. Okay? If you do the same with the Newton algorithm, you have to multiply by the number of points, and let's assume that it will converge in 10 times less iteration. I mean, that here it will converge in, let's say, 7 to 8 iterations, which is not the case. We can be optimistic. It will be around 243 days. Okay? Actually, it will be more than that. And if you want to be like, oh, brutal force, I don't want to think too much, I use MATLAB fsolve function, which is a very good algorithm. But this one is n-cube complexity. And if you do that, it will take about 1.5 million years. So I don't know, but me, I'm not patient enough for waiting a few million years. Of course, this is an extreme case just to make a point. We'll never compute that for practical application, but this kind of computation can be interested for conjecture, to investigate mathematical conjecture, for instance. So, to make a summary, we have a fast algorithm for computation on arbitrary depths, arbitrary wavelengths, large wave, but not the highest one. It was not designed for that. And we gave numerical evidence that Euler is equivalent to KDV for computation. And what will be interesting is to have serious mathematical insight. How it can be optimized and improved and this kind of thing. So we need mathematicians to do a serious work on this algorithm because it's fantastic. And I use two algorithms that are very efficient. It's the fast Fourier method and the perturbation method. I always say that fast Fourier transform is so efficient that you really need good reason for not using it. Okay? One good reason is when your problem is not periodic. But it's worth that you think about how to reformulate your problem in such a way that you can use it, because it will pay back. And now I have the same feeling for Petit method. The difference is fast Fourier method is much more known and understood from a theoretical point of view, while Petit, as far as I know, there aren't been that many progress. So, and you can read some paper about this method for solitary way that are published, one that is submitted for the periodic case. And the program is a MATLAB file that you can download for free. It's accessible on the MATLAB file exchange. So you can download it and use it. So I just want, so you can check by yourself the claim I made here. And I want to give you an example. So it's a MATLAB, it's live computation. Let's say I want to compute height over depth 0.4, wavelength 100 times the depth. That's the other parameters, and I call the function. Okay, that's it. It takes more time to compute the graphic than to compute the solution. Okay, and here I used how many? 1024 Fourier modes, and the computation was achieved. Computation time is 500 of a second, and it converges in 86 iterations. So, and you can use the value if you want. So that's the end of my presentation. Thank you.
So, what we do, they depend on the way you do these direct iterations to solve the problem. I mean, you use this Babenko equation, but that could be done using another formulation, or is that essential?
No, if you use the earlier problem, the way you take
like a boundary integral equation.
No, that's where. But
I mean, try to do this kind of iteration on.
It will not work. You need homogeneous nonlinearity. That's why we need a mathematical insight to understand how, when it works or not. So if you do it, you take brutal Euler equation, boundary integral.
Simulation, the linear part, non-linear part.
For example, if you do that with capillarity, you introduce capillarity, you have a crazy nonlinear term, it will not work. I didn't manage to make it work, and I've been trying hard because of the nonlinearity. And of course you can try to, perhaps I just got lucky. I never won anything in the lottery, so and it works so fine. I don't think it's just chance. So there is something behind that, but I cannot explain what. And,
sometimes it works, sometimes it doesn't. Yeah.
So it works. I mean, but you can try to tune, but you are completely blind. You are throwing the fishing rod. You don't know where, how. It would be nice to have some more theoretical insight to know how.
When these iterations.
Yeah, how and or how you can improve it. You have to work.
When you approximate periodic waves, the wave is unknown. How do you know what constant to subtract so that the periodic wave would be constant? But you don't know the minimum.
But it's part of the part of the algorithm.
So every iteration,
I subtract the minimum.
adjust.
Each iteration, I subtract the minimum, and I squeeze the amplitude to have the height I want. So it forces that. There are parts of the way and direct way. That's why you need to define your weight by the height. If you define your weight by another parameter, then you may be tricky. I haven't tried that yet. And again, there are many possibilities, but without any theoretical insight, I mean, you can go fishing for a long time. Fishing in the right lake.
So I didn't quite understand how you compute a different way. It was not the continuation.
No, there is no continuation.
So you just decide on some parameters and then.
No, I start here for this one, or even the 1 million. I didn't show the graphic. I start with a sinusoid here as initial condition, and at each iteration, I iterate, and I subtract the minimum to have the minimum as 0, and I scale the height to be the one I want. But there is no continuation. If you use phantom program for that, where you have to compute first an intermediate one, and you have to go step by step here, everything, the 0 or the the initial guess is the same for all of them. It's just the sinusoid that has the same height of that line. So it's quite far away. Can hardly call that a sinusoid.
But you could use your method with continuation. Then. You could use your method with
Of course,
Yeah.
of course you could. And that probably is what you have to do if you want to exceed the maximum point and you want to go. Of course you could, but I didn't do that. And I think what you can do here that you couldn't do before, I think, is the long wave, because they were too expensive numerically. If you wanted full precision.
So why can't you exceed the first maximum? It's because of the choice of
Because
the
it's not the parameter you have to compute has two possible values. It doesn't know which one it should take. This is my explanation, but I will not bet my life on it. But this is my understanding of the problem.
And in your code, it's not obvious to change parameters. To take
No, you have to start. You have to you could do a meta code with several pairs of parameters to define the wave, and you think, it's not converging. Then I change, I rescale. But this is a more complete. Not for practical engineering application. But of course, this is what I have in mind for future investigation, but I couldn't do it. There are many things, many possibilities.
Can you put multiplicity on these things?
For Pedviashvili, I don't know, but for Babelko, yes. For Pedviashvili, I think with constant vorticity, it may work. But it's not out of the box. It's not just I take my equation, I threw it in the Pedviashvili. No. You have to understand the method, you have to pay, you have to work to cast your problem into a form that will be suitable. While when you use the Levenberg-Macal method, for example, you take your equation, you fit directly, and it may work. But it comes at a price. Thank you. So this method is very tailored for a problem. But you have to do that. As I mentioned, you can easily and when I said 100 seconds, it's on this computer. I don't use supercomputers. It's on your laptop. And with the algorithm, you can implement it on a smartphone if you were to go to the film and wait the work time. It will converge in reasonable time.
As I understand, you can compute the solution shape with accuracy as good as you want.
With precision.
With precision.
Yeah, because when I said you reach spectral precision, it means the Fourier mode of the magnitude of the working precision. But it doesn't mean that the solution, because when you have a lot of, so when I use 1 million Fourier mode, okay, the highest frequency of magnitude of 10 to the power minus 16, but the error is more about 10 to the minus 12, because you have random error. So don't confuse accuracy and precision.
But my question is, so philosophically speaking, it proves nothing. So
it proves nothing mathematically. You have to convince yourself.
So that is the, okay, you can compute, but you cannot say that this is what you want. Or
no, but what you can do.
I mean, rigorously speaking, right?
No, it's not a mathematical proof. But
so
this equation is not trivial from a mathematical point of view. But what you could do with this algorithm, you can use interval arithmetic. And it will require just a little bit of modification, and you will have an idea of the mark. It will give you error bars for your estimated solution, if you want to gain more confidence. And here I have nothing else to compare with, so I just have to look at the Fourier spectrum, and because I don't know of any other. There are no other, but I compared with some new exact relation analytical formula I derived recently. They are not published, and it matched to at least 6 digits. But I don't know if it's because this one was not accurate, or it's because numerically I compute the formula because they are completely different formulas. So
once in the lectures about the statistics of waves, and to collect statistics, you should compute for a long time period.
Yes.
And could be not complicated equation, but for a long time. And actually, what's at the end or after 10 seconds of computation, nobody knows. So it could be completely numerical result.
Sasha, I've been showing in floating bodies 15 years ago some fast computation, long-time computation, with thousands of periods.
Yeah, it's possible, but there is a kind of special technique to do that.
And you have nothing to compare. So to convince yourself, what we do, we go backward in time. And I've been showing, I don't know if you remember, but after 1000 period, you go back in time and you find the initial condition. The difference is just machine precision. So I think it's fair.
Yeah.
But it's not a proof.
No.
It's not a proof. It's not a mathematical proof.
But as you said, know that mathematical technique or mathematical proof that what we are looking for, it's there. I mean, that just I'm always confused with that mathematics and computations. So, so it's.
But when you do this kind of stuff, you cannot wait until mathematicians have proven rigorously, because then you will never do anything.
Sure.
And I understand. I'm not. I mean, it's logical. It's difficult.
Yeah.
But aren't there proofs, I mean, for global bifurcation?
Would exist
There are
as a
some
solid.
solitary ways going back to Friedrichs.
Yeah, or Lavrentiev.
For the order?
Yeah, proof of existence.
Yeah, proof of existence, doesn't mean that.
It doesn't tell you what it looks like.
Computation.
Yeah.
It's all certainly for gravity waves.
So I would be kind of just thinking about what we could expect to get, right? So to go somewhere, we need to know where we're going, right? So if we say, okay, that is the solution, and we can prove that there is the actual solution. This is one story, so existence, right? And also we can prove that the difference between that numerical solution and actual solution, even we do not know that actual solution, we just approaching to that solution. The difference is, okay, let's 1 divided by 100, for example. No need for 10 in the power minus 1 million. No need, just small, but to be sure that it's there. Right? So this is the, as I understand, it's still somewhere, still not without.
I can just repeat what I said in the beginning. You can compute that with double precision, then you compute the same in quadruple, octuple, and you see that the digit match and the increase. I can be fairly confident that it's not completely silly what you're computing, you know. But it's not a proof. But it's a strong numerical evidence.
There is name for this. It's like truth-like arguments. They looks more and more reasonable. If you go to 10 to the power minus 1 million, it's very reasonable, but it's still
in a number theory, they have a counterexample that appear at 10 to the power 10 to the power 10 to the power 1 million. You know, and you have in arithmetic, you have this kind of paradox. But okay, so it exists, but I cannot tell you it doesn't happen here. I just think it's unlikely. Because also it's physics, it comes from physics, you can continue parameter, you get sensible.
Yeah, it's another story.
You have other, not really mathematical, but you have other kind of arguments that, okay, you can feel pretty confident about what you think. But if I would agree, if you just can get 2 or 3 digits and you cannot exceed them, because actually it's quite easy to compute the 2, 3 first digit. It's after that, it's getting complicated.
But if we can compute 3 digits and we can prove that they are right,
but you have to prove it.
That's quite enough.
But if you can prove it, that's the point, is that you cannot prove it. Of course, if you can prove.
Okay, this is a discussion for